Section 6.8. We are going to do Lagrange's method, but before that we have to set up the problem of how to solve extreme problems with constraints. What I mean is something like this. Suppose you have a function that's called f x, y, z, and it is under a special constraint that's called, for example, g x, y, z equal to some constant k. Now the question is, what if I want to find the maximum or minimum value of f under the constraint of g, such that x, y, z has to satisfy the g relationship, but I want to know under that constraint, when does f go to be the maximum or minimum value? Now, there are several ways to do that, of course. The common way is simply do a substitution. That is, you solve for one of x or y or z equal to a function, and then plug it in there, and then take your partial derivatives and so on. There is another way. It's called the method of implicit functions. That is, we don't directly solve for it, but we just take everything with partial implicitly. Take the partial derivatives and see how that would work out. Which means, for example, that suppose we have a solution. In reality, it has a solution, but we're not going to work on it right now. Say z solves for x. Z can be solved in terms of x and y from this particular equation. So you know it can be done. And then we'll take the partial derivatives of all this and see where it leads us. So what we have is then you plug z equal to fxy into here. So you have then, and you set this particular function, let's say u equal to f of x, y, and z, which is f x, y. Okay, so you plug it in, and then you take the partial derivative of u and set the partial derivatives to be 0, and then solve for something to see if that gives you any maximum or minimum values. Because you know that if there is a maximum or minimum, it will set at where u is, well, under certain conditions, of course. So then from here, we are trying to solve something like this, equal to 0 and the same as y, partial u, partial y equal to 0. Now to do that, we will, right now we don't have any specific examples, so we're just doing things in general. So let's see how far we can go in general. Now to solve for this, given that u is this thing, we know that partial u, partial x, cranking it out from here with respect to x, is going to be f1, okay, plus f2. Y is a constant with respect to x, so that's 0, and then f3 times this will be partial f okay, partial f partial x, which is the same as partial z partial x, because z is f, and which is going to be equal to 0. And similarly, we have the other one, partial u partial y equal to, with respect to y, you just change one thing pretty much, is that then equals to f2 plus f3 partial f partial y. And then we'll do a similar thing of plugging in there. We will have plugging z in here. We have g of x, y, and fxy minus k equal to 0. And we'll do the exact same thing here. Doing the same thing here, doing the partial derivatives for this, we get something like this. Then with partial u, partial x, well, actually, we'll just take the partial of this thing, because this thing is actually identically 0. Okay, it's called a totality, I think. Anyway, this thing is identically 0, so we'll take the partial derivatives of this. So we have g1 with respect to x, so that gives you g1 plus g3, and then partial f partial x which is going to be 0 because this thing's identically 0. And then similarly, we get G2 with respect to y, we get G2 plus G3 partial f partial y. And that will give us 0. So now we have this thing and this thing. We have two sets of equations. So then what we're going to do is this gives us what partial f partial x is. So this thing is simply equal to minus g1 over g3. And similarly, the partial f partial y equals to minus 1 g2 over g3. So then we'll plug these things in here to give us a bunch of stuff. We'll work on the first one. The first one gives us f1 plus f3 times this stuff, negative g1 over g3. This is going to be equal to 0, and where if we set partial u partial x equal to 0, that's where we're getting this from. Gotta remember what we're doing here. So then, so what does that give us? This effectively gives us, under proper conditions, for example, G3 cannot be 0, otherwise this doesn't make any sense. So assuming all the proper conditions are satisfied, we effectively get, what we get here is that, let's see. Okay, effectively what we get is G3 F1 minus or equal to F3 G1. That's what we end up with. And similarly, we can do with this one, it's just the 3's and end up 2. We replace 1 with 2. Okay, I see 1 with 2. So then but everything else is the same. So we get G3 F2 equal to F3 G2, and that's the relationship for finding the partial derivatives to be 0, which means that, I mean, look at what this means. This means that the functions have a set proportion. That is, what you can come up with this is f1. If you solve for f1, we see the f1 equal to f3 divided by g3 times g1. Similarly, f2 equal to f3 divided by g3 times g2. And of course, f3 for sure equals to the f3 divided by g3 times f3 times g3, because, well, that's just how it is. So in other words, the ratios f1, f2, and f3 is proportional to the ratios g1, g2, and g3. And what that means is that the directional normals are the same. So they are pointing the same way. And that's what we say when the maximum happens, is when the directional normals are going to be identical on the two surfaces when you set f at that particular maximum value. Now, out of this particular relationship, the fact that they have the same proportion, okay, f and the three f's and the three g's have the same proportion, we're going to come up with something called the Lagranges method. The Lagranges method is a way of calculating these maximum and minimum problems. It's a very systematic way, which we'll do in the next video.